400 picoseconds against roughly 40 nanoseconds? That gap, 100,000 times, is the write speed delta a Chinese university lab posted in early 2026, and it sits beside a shelf count of 0 units. One dial reads the physics. One dial reads the product. The roadmap from here traces how far apart those two dials are and why the wall that was supposed to prevent the first reading may have selected for it instead. Before 2024, no Chinese laboratory had published a direct cell-level write speed comparison between a graphene flash cell and shipping NAND flash. The research existed in journal papers, but the head-to-head number did not. Yield data on graphene memory pilot lines was either absent from the public record or reported in ranges too wide to carry weight. The metric had no usable first reading. The gauge had no needle. In early 2026, Fudan University published a write speed result of 400 picoseconds per cell. Consumer NAND flash drives operate in the roughly 40 nanosecond range for single-level cell write latency, an approximate figure drawn from the standard range across the industry rather than a single manufacturer's specification. The ratio derived from those two published figures is 100,000 to 1. 100,000 times. That is the headline delta, and it is a cell-level lab measurement, not a drive benchmark, a distinction the rest of this script will return to because it does more work than the ratio itself. Separately, Atom2CHIP, a Shanghai-based graphene memory startup, reported a 94% yield on a pilot fabrication line during the same period. That is the company's own figure, not independently verified by a third-party fab audit. The two numbers come from different organizations measuring different things, and placing them beside each other is not a coincidence of timing. They are the two dials on the same instrument, and reading them together is the only way to understand what the metric is actually measuring. The speed gain is not an engineering trick applied to a familiar substrate. Graphene's electron mobility is intrinsically higher than silicon's by a wide margin. The result at Fudan reflects a material property, not a process refinement. When the conventional path toward advanced memory performance runs through sub-10 nanometer silicon patterning, through extreme ultraviolet lithography tools and advanced etch chambers and deposition systems that the major Western equipment suppliers do not sell to Chinese fabs under current export controls, the engineering effort does not stop. It moves. The restricted equipment chain that governs advanced silicon node production is, at the pilot stage, partly irrelevant to graphene flash fabrication. Graphene memory at the current development stage does not require the sub-10 nanometer patterning that makes extreme ultraviolet lithography indispensable for silicon NAND. The fabrication steps that matter most right now are deposition quality and interface control, achievable through chemical vapor deposition tooling with a meaningfully different equipment profile from the controlled list. The export controls were written around a specific map of how advanced memory is made. Graphene flash is being built on terrain that map did not cover. This is the material choice argument, and it is more load-bearing than the speed number alone. The 100,000 times ratio is striking, but the more durable fact is that it was produced without the tooling the controls were written to deny. The wall selected for the result it was supposed to prevent. The physics ceiling on graphene is genuinely different from the physics ceiling on silicon, and the engineering redirection landed exactly there. Whether that outcome was anticipated by the architects of the restriction is a policy question the measurement instrument does not answer. The gauge only records that it happened. The yield reading at Atom2CHIP does opposite work on each side of the argument, and that tension is worth sitting with. 94% sounds like a success. For a pilot line on a novel substrate with no established process baseline, it is. But volume NAND production at the leading fabs runs at yield levels that took more than a decade of accumulated process learning to reach, and even small yield degradations at volume translate directly into cost per bit figures that determine whether a product can compete on a shelf. The 94% figure is not a floor confirmed under volume stress. It is the ceiling of what a pilot line has demonstrated under pilot conditions. The lot sizes, wafer counts, and thermal cycling conditions of a pilot run do not replicate the sustained pressure of volume production. The number has not yet been asked the volume question, and the instrument cannot report an answer that has not been measured. The gap between 400 picoseconds and a shipping unit is not the same gap as between a prototype and a factory. It is closer to the gap between a land speed record set on a dry salt flat and a car that can be driven on public roads. The salt flat removes variables, flat surface, controlled conditions, one precise measurement taken under optimal circumstances. Public roads reintroduce them, Corners, weather, other vehicles, wear over time, regulatory approval built across years of testing. The 400 picosecond reading is the salt flat number. 94% yield on a pilot line is the first stretch of public road. The rest of the road has not been built, and no public timeline exists for building it. 3 readings on the margin of error deserve explicit reporting here, because the instrument would be flattering the trend if it reported the 2 headline numbers without them. The first is the gap between claim and independent proof. Both the 400 picosecond speed result and the 94% yield figure come from the organizations that produced them. The Fudan speed result was published in a peer-reviewed context, which adds one layer of scrutiny, but peer review of a laboratory result is not the same as independent manufacturing verification by a separate facility. The ATOM2CHIP yield number is company-reported, full stop. Neither has been confirmed by a third-party fab audit, and no second laboratory has publicly replicated the Fudan conditions and obtained the same figure. The gauge is reading its own output and reporting that reading as the measurement. That is worth stating plainly. The second is the range of physical variables the speed number does not capture. Write speed at the cell level is one of roughly a dozen parameters that determine whether a memory technology is usable inside a real system. Retention over a working temperature range, endurance across thousands of program erase cycles, read-disturb behavior when neighboring cells are accessed, array-level leakage current at scale, and the thermal profile of the cell under sustained write loads are all separate measurements from the write speed figure. The 100,000 times ratio is real for the single variable it measures. The endurance delta in particular is the unseen counter reading. A cell that writes in 400 picoseconds and then fails after a small fraction of the program erase cycles that consumer NAND handles routinely is not a product. The published literature on graphene flash endurance figures is mixed, and the independent verification gap on those numbers remains wide. The most recent Fudan work reports endurance improvements, but specific figures in the published record have not been independently closed. The speed number does not speak for the endurance number, and the endurance number is where shipping NAND has the deepest accumulated advantage. The third reading concerns density and cost per bit. Consumer NAND ships at storage densities achieved through decades of lithographic scaling and 3-dimensional cell stacking, with layer counts at leading fabs reaching into triple digits. Graphene flash at the pilot stage is a planar technology. Cell densities are not publicly reported in directly comparable terms against volume NAND. A memory device that writes 100,000 times faster but stores a fraction of the bits per unit area at a cost per bit that is orders of magnitude higher is not a replacement for what sits on a shelf today. The density and cost per bit delta does not yet exist in the public record as a number, and its absence is itself a data point. The instrument cannot report a reading that has not been published. The synthesis across those 3 points is this: the speed reading is load-bearing and the yield reading is real, and both are early-stage readings on a technology that has not yet been asked the volume questions. The delta between the physics frontier and the manufacturing frontier is wide. The delta between the manufacturing frontier and a competitive shipping product is wider still, and that second gap carries no dated second reading anywhere in the public literature. Following a single unit through the chain makes the gap concrete. One graphene flash cell, written in 400 picoseconds under controlled lab conditions at Fudan, demonstrates the physics. That same cell must survive hundreds of thousands of program erase cycles without degrading its threshold voltage window to the point where the controller can no longer distinguish a stored charge from the absence of one. It must hold its charge over a temperature range representative of the device operating in a data center or a consumer product. It must be patterned alongside millions or billions of neighboring cells without disturbing their stored state when it is accessed. It must be stacked or arrayed or otherwise multiplied in 3 dimensions to reach the bit density that makes the economics of a product viable. It must be tested across multiple wafer lots at volumes that stress the deposition process in ways a single pilot run does not. Each of those steps adds a measurement the current published record does not contain. The cell exists. The product does not yet have a path with a dated milestone. What the 2 dials together show is a technology that has cleared the physics test and is somewhere early in the manufacturing test, produced under the specific conditions created by the restriction that was supposed to prevent it. The lab number is real, the shelf number is 0. Those are not contradictory readings. They are the expected readings for a platform technology at this stage. The fact that they were produced inside the restricted perimeter rather than outside it is the conclusion the raw figures do not state but the measurement supports. The export control did not stop the speed reading. It selected for it. When the conventional path, advanced silicon nodes, restricted lithography, controlled deposition systems became inaccessible, the engineering effort moved to a substrate where none of those tools are the binding constraint at the current development stage. The wall did not freeze the metric. It moved the metric to terrain the wall was not built to cover. That is not an argument about the wisdom of the policy. It is a reading of what the instrument recorded between pre-2024 and early 2026. 2 dials, 1 reading each. The speed gauge is 100,000 times ahead of the shelf, and the shelf is the only gauge that ships. The question this metric will answer by late 2027 is whether any graphene flash line crosses from pilot yield to what the industry recognizes as pre-production qualification, meaning sustained yield across multiple high-volume wafer lots, under conditions that replicate the stress of production at scale. If that crossing happens, the next reading worth tracking is which system integrator puts its name on the first bill of materials that includes a graphene flash component. That is the measurement that would move the second dial. It has not moved yet. If you follow the distance between lab readings and shipping readings in deep technology competition, subscribe and turn on notifications. The next delta in this series measures a different material and a different shelf.